Hi. Look, in this video, we're going to look at the derivative from a different perspective. We will think of the derivative as a measure of the slope of the function at a given point. So basically, we're going to be talking about graphical representation of the derivative. Okay, and look, let's consider a case like this. Here is short-run total cost function. I don't know whether you already learned about it in your microeconomics class, but this is how this function looks. You can think of x as the level of production of the company, or y as a total cost. Okay, and look, we've learned that if, let's just say, we start at some point x0, and you're wondering about how the cost in your company is going to be changed, right? And let's just say that you are considering what is happening between point x0 and some other point x1. Okay, again, we can start our consideration by using a difference quotient. Right? Okay, so how do we go about it? Look, we see here that this is delta x, and here is delta y. This is by how much x has increased and by how much y has increased. And it makes perfect sense. The more we produce, the higher should be the cost. Okay. Now, so in this case, we can again use the right angle triangle and the slope of this hypotenuse in order to approximate the rate of change. But look, what is the problem with this reasoning? Look, here we see again that the short-run total cost function is curvy. Here is actually increasing faster and faster and faster. So look, if I'm gonna be approximating using this line, I can say that this area over here represents the measurement error. Because look, I will obtain some average rate of change, which will be 100% correct if I'm considering those 2 points. But actually it will mask what was happening on the line. So now the question is, what could we do to make our measurement error smaller? Well, the trick that we used before went like this. Well, we decided to choose some different x1 and a different point. And see what happens as a result. Look, first, delta x has gotten smaller, right? Now we've got this new delta x, the green delta x, and new delta y. Now, I hope you can see that if I connect those 2 points, then the size of the measurement error has gotten way, way, way smaller. And look, if I would take this picture and put this in a magnifying glass, just this part, what would I see? That if our starting point was over here, right? Then we had this big triangle leading to associated with point x1, and here's our x0, and this triangle was characterized by this big measurement error. Now, when I've introduced lower x1, I'm sorry, this is of course x0, and when I introduce lower x1, just say here, then this triangle has become way smaller, and because of that, we see that this measurement error got smaller. And look, but this measurement error still exists. So we still get some average value. So what was the trick we used when we went with derivatives? Well, maybe we should use even a smaller triangle. So we should choose smaller x1. Yeah. And we would give them smaller delta x. And look, this would be, again, a move in a good direction, right? Because you can see now that this measurement error has gotten really, really, really small. Now, but it still exists, right? So again, let's go back to what we said about derivatives. In order to eliminate this measurement error, what do we need to do? Well, maybe the change in x we're going to exploit should be extremely tiny. How tiny? Well, I hope you remember that we can think about this change as here is one point, some point x0. This point is so tiny that it doesn't even have a size. Of course, I cannot draw anything like this. Plus, you wouldn't be able to see if I even could, although it's impossible. But then I can imagine that next to this point, there is another point, x1. Also, no size, so it's extremely tiny. So look, what we can use is a situation in which we move away from x0 to x1 by dx, which is equal x1 minus x0. But look, we are moving by such a tiny distance that it even doesn't make a difference. Okay, but there comes another issue. Well, this issue is that, look, if we gonna use such a tiny increase, then how can we get the hypotenuse of the triangle? Because look, here we had hypotenuse by establishing some delta y, establishing some delta x, and connecting adjacent to one side of the left side of the adjacent with top side of the opposite by hypotenuse, and this hypotenuse, tangent alpha of this hypotenuse, was giving us a difference quotient, right? It was a ratio of delta y to delta x. But if we're going to be at a point, and we are moving so little from this point that we are basically staying at the same point, how can we accomplish that? Well, look, as it turns out, it's not such a hard task to do. Because look, if I want to know what would be the angle of this curve at one particular point, what should I do? I should simply draw a straight line. I'm sorry, you couldn't see it here very properly, but it's really hard to draw. But look, I could draw a line that is tangent perfect. I would draw a straight line, that is tangent to this function. And remember, what tangent means that it touches the function just in one place. But now, okay, you say, okay, so we've got the hypotenuse, but what about the adjacent and the opposite? We do not have delta y and delta x. But can we create some? Look, over here, I could just draw some adjacent and some opposite, and say that this is delta x, this is delta y. But then we would say, probably, or maybe not, that, okay, but I've chosen those arbitrarily. Why I didn't choose, for example, longer delta x and consequently longer delta y. Of course, those two are occupying the same space. I just draw this so you can see. Okay, valid point. But this should remind us about some other theorem, Thales theorem. And what would this theorem tell us? That if you're gonna take blue delta y and you divide it by blue delta x, you're gonna get exactly the same number. If you're gonna take, this is either pink or red. Okay, I'm gonna say pink. This is by pink delta y over pink delta x. So look, actually, we would get here exactly the same outcome. Doesn't matter what is the chosen delta x, because the corresponding delta y would take such a value that all possible delta x's, all possible delta y's divided by delta x's would give you exactly the same outcome. And look, so now we know how can we calculate, how would we calculate the slope of the function at a given point, right? We can just use a tangent line and calculate delta y over delta x. But do we really need to do it? Maybe there's another way to do it. Well, of course, we remember that the ratio of opposite to adjacent is equal to tangent alpha. Well, that's an interesting piece of information. So we know that if we know the slope of this line, we can use tangent of the slope to get exactly that. But look, we can go even easier. Look, this is a straight line. So look, the slope of this line is given by its coefficient, right? And look, what do we know? Look, this function is curvy. What does it mean is that, look, the curvy line has a different slope at every different point. Straight line has exactly the same slope at every point. right? And look, in this place, those two lines are tangent. So those two functions are tangent. What does it mean? That out of all different slopes of this line, only at this point, no, but it's not necessarily true, because actually I could find a parallel line that would have a similar property over here. But in this area, where the function is growing faster than proportionally, this is true. Only at this point, the slope of this line and the slope of this function are exactly the same, right? So if I know the slope of this line, I will know the slope of this line at this point. Okay, but then you can still pick more holes in my story. Okay, we are taking that this is true, but this function over here has infinite number of points. Then what does it do good to me if I know the slope just as one, at one point? Well, of course, valid argument, but look, if I know how to do it for this point, then I will know how to do it for every other point at this function. And basically, this is what we do when we calculate derivatives. Look, if I know the formula for the function y equals f of x, then if I'm going to calculate f prime of x, what am I obtaining? I'm obtaining a new function. And look, depending on what I'm going to plug in inside this function, I will get a slope of the previous function over here. Look, in our case, if this is short-run total cost function, then the first derivative will give you marginal cost function. And by putting a different level of production, you will get a slope of derivative, a slope of the total cost function at any given point. So look, by calculating derivative for a function, we are obtaining like a set of all slopes of this function. Okay, but now, okay, so look, if you calculate the derivative, you have a function, you're obtaining a different function. You might ask, but what if I want to know what is the what is the slope of this function at a point where x is equal to x0? Well, nothing more easy. This would be just to put x0, the one that we've got over here, inside the derivative, and what we are obtaining? We are obtaining the same thing we would get with tangent alpha, or with delta y over delta x. But then, of course, from this graph, remember, this is the blue delta y over delta x. And of course, here we've got tangent of tangent alpha for the blue line, which I denoted with a green color. And this, what you see over here, is the slope of the function at x0. And look, by the same reasoning, we can get that if I replace x1, x0 with some other point, x7, then I will obtain slope of the function at x7. So, once we've learned how to calculate a derivative, we will be able to find the slope of the function at any given point. Okay, so this is what we're going to do next. But before we get to calculating derivatives, we need to learn a couple of rules. How to calculate them easily. And for that, we need to review another topic. Because look, we already said that derivative is defined as a limit with delta x approaching 0 out of a difference quotient, right? So maybe before we get into calculating derivatives and finding those easy rules to calculate derivatives, we should start by reviewing the limits. And this is what we're going to start in the next video. Okay, so take care.